Hey, hello. Just gonna grab it like that because it's so yeah, I'm Michał. Some people call me Wheels of Fury for reasons that I don't really understand, but that's a really cool picture from International Space Station. I really like it because it shows both of my homes. I was born and raised in northern Poland, and 4 years ago I moved to Sweden. So I like to say that I whole life lived in the north. I moved more north, and now I live in the south of Sweden. So yeah, about the title of the talk, it's a bit of a lie because if you if you will do any serious machine learning, you won't be able to run out from the math. But the math is not that hard, and I'm just gonna try to show you with basic developer terms that it's really not that hard math. It's like there are much bigger problems within machine learning than mathematics. Um, do we have any data scientists on board here today? All right. Uh, any people with, I assume that's answer already, but with engineering degrees? All right. You're slightly overeducated for some part of this presentation, but that's okay. Um, so first, let's start with machine learning, artificial intelligence, all those things. So people tend to call artificial intelligence things that are sort of like smart, artificial, obviously, and they don't fully understand. So at the beginning, we had first computers that were made in the 40s. For most of the people, that was magic. That was some artificial brain that we had a lot of expectations. They were initially designed for calculating ballistic tables for artillery for United States Navy, like ENIAC, but turn out they can be used for multiple other tasks, and people started using computers. Sometime later, we had computers playing chess, and it again felt very smart because you know, it was beating humans at game that was sort of seen as a game of smart people. But again, right now we know that's it's completely doable to put all the possible chess moves in store them in computer and just play optimal moves based on the current state of the game. There's like no magic here. So right now things like Watson or AlphaGo are things that we see like artificial intelligence because we don't fully get how they work. They're doing some magical machine learning stuff that nobody knows what they do. So we'll try to look into a bit how those things works and show you, like, try to bring down into small pieces the one basic algorithm that used within a machine learning space. Generally, algorithms used in ML are divided into, there's like few ways to classify them. The biggest one is probably to classify between supervised and unsupervised learning. Supervised learning is the biggest part of this all right now, and the one that's gaining the most press, and it's the most popular. This is the sort of thing that we feed to algorithm a lot of examples with the data and the right answer. For example, a lot of pictures of cats and other animals, and you label them that that's cat, that's not cat, or wherever we're doing, or we're feeding into the algorithm the transactions, and we're saying this is the good transactions, this is like the fraud transactions. So that's, for example, what's used in banking to discover fraud transactions on credit cards. And then algorithm builds sort of like a connection within itself to what's pretty much learns what are the good data, what is the bad data, and when you feed the new pieces of data that's without label, it can give you some approximation. Is it like a cat or non-cat, or is it like a good transaction or bad transaction, and so on. Unsupervised learning is I think it's much more interesting, but it's still very non-developed because this is sort of, you feed the data into algorithm and you get some answers. So thing that you can do right now without supervision. For example, finding common categories. You get feed the base of your all customers from your online store, and you get them feed into some clusters that have similar behaviors, and then you can use this data in some way. For example, for a recommendation system or something like that. What's really important about it, because you don't have this whole step of feeding the data with the right answers, and you have manually labeled the data, it's this sort of algorithms are like much more more automatic, because there's not much human interaction here, and that's why a lot of people who are engaged in that field, they believe that's where the future lies. Like, so more work with unsupervised learning. And there's also a thing that's sort of like between, so it's called reinforced learning or reinforced algorithms. You use some sort of state. You have some word, for example, game of chess can be a word you use, like a state you use, and then the algorithms try to make some moves in this word. For example, like moves the pawns filled up, and you give the feedback: is it a good move or a bad move? So it's sort of similar in the supervised learning, but it's more like interactive. Like there are steps, and you do like generation of steps. So you may be seen on YouTube or wherever videos of machine learning playing Mario games and just basically getting better and better and better. That was like one of the example of supervised learning, not supervised but reinforced learning. It's just that it wasn't a human who was just giving the answer. It's like a good move or bad move. It was just based, for example, on points or like passing the levels and so on. So it could be fully automated. So there's like a lot of interesting sandbox in the internet that you actually build those algorithms by yourself and play with those things. And I think like playing the classic games is like the most popular also among nerds of us, because it's like play on this emotional note of us, the games we used to play. Okay, so today we're gonna touch linear regression, which is like I think one of the simplest possible algorithm you can use for machine learning. It's become later based for doing neural networks, but we're not gonna get there. But a lot of the math we're gonna talk about also find application in neural networks. So this is the part that's kind of many of you are overeducated for. But let's first just look on how you can chart two-dimensional data in space in a flat space. So that's the common way to chart a lot of data, where you have some values of data depending on some parameters, or just looking at speaking developers terms, like that's how you can chart function that takes one argument and returns some value. So for every parameter we have some value, and that's how it's chart. On horizontal axis you have parameters, on vertical you have the value for that parameter. Also on two-dimensional chart you can chart linear function. This is sort of function that's straight, and for every possible parameter there is some answer for it. So it's not even points. The points are so dense that basically creates a line. And it's important that it's straight, so it's like very simple function. That's and this function can be described like the line by two parameters, which is a and b. A is the angle of which the function is sort of angled from the 45 degrees or wherever, and b is how high is moved from on the vertical axis. So if you use, for example, the example I had here, that over age, the older you get, you more money has in your bank if everything goes well with your life and so on. Then if a equals 1, this is like 45 degrees. This means you have like steady income over life. That's great. If a bigger than 1, you probably have a better job and your income is quicker. So that's a good example if you have like a better job, for example, software developer. And with b bigger than 0, you have a much better start to your life. So I don't know, you had rich parents or were born in Sweden. For the purpose of machine learning, we're not gonna use the general terms like A and B that's used in mathematics. In machine learning, we use W and B. That's just, those things are pretty much interchangeable, but just so you know, if you read some literature, and W is weights and B is biases. I'm not gonna deep into what those things mean right now, but just if you ever look into some articles or scientific papers and so on, most likely you'll see this designation used instead of A and B. But just, yeah. Alright, and yeah, weights and biases, as I mentioned. Okay, so today our mission is to figure out what characteristic of wine impacts its quality. I'm gonna use the dataset from University of California Computer Science Department. This is a CSV file. I just opened it in Excel because it's more clean to read. We have 8 or 9 parameters of wine, and also quality, how people felt about this wine on average. And the quality here is our label. So this is like we're gonna do supervised learning, and the quality is our right answer. And now we're gonna train algorithms that, given one or more of those parameters, will kind of try to predict what's the perceived quality of this wine. And as I said, we're gonna use the linear regression. And linear regression is pretty much trying to fit linear function to your data set. And for the simplicity, we're gonna use right now just one parameter, so we can show everything on two-dimensional data. But optimally, you want to use as much as features as possible. So the features are those parameters I mentioned. So it's things like acidity, pH, chlorides, amount of alcohol, and so on, density. Okay, so how are we gonna fit this? Basically, the way it works, you start with function at some point. It can be, for example, flat, so a equals 1 and 0 and b equals 0. And we'll try to fit this function as well as possible to data. So sort of this looks like decent fit. And the way we're gonna do it, it's just gonna do start with like some random point, or not even random, just 0, 0, and calculate our error function, so how far we are from the perfect solution, and try to make a step into a direction that's better. Again, calculate the error function and so on. So error function is, or cost function, this is also used interchangeably, is a function that says us how badly we are not matching the function, how are we free from like the perfect fit or nearly perfect to the data. And it's calculated by something called mean squared error. So this is the first math today, probably the most complicated math we'll see today. So looking into more human or even more developer terms, this Greek sigma sign is pretty much for loop. So for every element of our example, so of every data point we have, we calculate what's the difference between our prediction and the actual answer. So y is the actual answer, h0 of x is our prediction, and we square it, putting it to, and then we sum it up all, because sigma is pretty much like summing it up, not really for loop, but sum of everything. But yeah. Why do we do square? So square has two functions here. First, it doesn't matter if we're like below or over the function, we're always gonna get plus sign, so it's a good thing, because when you square things, you always lose the minus sign, or the sign at all. And the second thing is, with square, the more far away you are from the actual function, you get even more penalized. Like with linear, this you get just like penalized a bit more, but with square you get just the more far away, the you get penalized squarely. So let's try to write some code up to this moment, and then we'll try to see how we actually optimize this function, so we find the functions that actually fit the data best. Alarm! Alright, we're saved. Thank you, Michael. I'm using F#, but it doesn't mean you have to do it with F#. C#, or whatever programming language you're programming with is good enough. I use F# for two actually particular features. First is interactive mode, so I can write anything here, and it will be evaluated. So it's like a lot of languages also have, like Python or Ruby has also REPL, and it's very good for like building programs. You don't have to like write everything that compiles, but you can like build it step by step and in a more interactive mode, which is nicer if experimenting with things. You can also like mark the whole lines or multiple lines and just run them here. This is just for referencing some packages I'm gonna use, so it doesn't really matter. Second important thing I'm using F# for is the feature called type providers. It's very nice way to use the data that's in a not very structured or organized way, for example, or maybe actually structured and organized but not strongly typed data. So for example, you have text file in CSV form, or XML file, or a website that you want to parse. And type providers can parse this data and give you back something that's strongly typed. So I can now load this file that I showed you previously into type provider, that's a CSV type provider. I'm gonna take just first row from this. Well, what I'm gonna get here is pretty much like rows of data in here, and now I can take first row of this table and do like access the things that were in Excel in like text file in form of strongly typed. So for us who people who are writing like .NET or Java and like to do what I like to call type-driven development, so you press dot, dot-driven development. So you press dot and you get all the possible ways. That's a very nice feature, because you get it works without compiling, which is super nice, and that's what I'm gonna use now. Alright, those are some options I use for charting. So we can chart all the data we had already, hopefully. Let's try it again. Something didn't quite work out. Let's go all the way. That's not good. Wonder if I have any data here, but I should have some data, because I'm just gonna maybe, because it's using Google Charts, yeah. That's this one, right? Good point, somebody. Let's try again. Yep. Good point. Alright, so I didn't show you one thing. I just picked one one parameter to chart. So this was like per alcohol. Let's chart the citric acid. The chart. Yeah. Okay. So what we have here is how much of the value of the one of the features I picked and the quality that was perceived. So because I'm gonna use just one of the features to have the simpler calculation and basically simpler visualization, we could visualize with two parameters because that would be three-dimensional charts, but more it's pretty much impossible to visualize those things. But mathematics works anyway with multiple dimensions, so just for the sake of visualization and just a slightly simpler math, I'm just going to use one parameter, and I know for a fact that to have a nice linear matching, seems like alcohol is a good fit. Like the more alcohol you have, the better wine it seems it is. So now we're gonna try to build algorithms based on that, and also at the end we'll see how good prediction was that. And yeah, let's get back to code. Alright, so first thing we're gonna do, when you're gonna work with machine learning algorithm, actually most of the work will be around the data, because you won't get the fully specs data and so on. Fortunately, this is like the full, the data here is like complete for every row. We have all the parameters and so on, so that's not a problem, but quite often you have that problem. And you have to just do what you can to fill those gaps, but sometimes you won't be able. And the second thing we need to do when we're preparing the data is like you want to divide data in a couple of sets. Either it's like 2 sets or 3 sets, depending on what you're gonna do. We're gonna divide it here in 2 sets. First is gonna be the learning data, so the set I will use to teach the algorithm, and the second set will be data we'll use to test if the algorithm is doing okay. The reason we're doing this, we don't want our algorithm to get too well to work on the data it has seen, because then it's not very general. It's sort of like when you learn to the exam, for example, for a driver's license, and you memorize all the questions. Like when you see all the questions, you can memorize all the questions, and you're not very general at solving the problem of like knowing the rules. You just memorize the question, and we want the algorithm to work also very well on the data that it hasn't seen. So it's more about finding a good fit of functions, but not too good, because then it's like too specific. It's called overfitting. And one of the ways to avoid it is just split the data, train it to at the learning data, and just compare if it's still working well on test data. And sometimes if it's not, you probably maybe want to retrain it at a bit less intensive setup. Also write the function that's our predict function, and it's a very simple function because this is the linear function wx plus b. I'm just gonna take 2 parameters and give the output. And also the cost function, which I showed you before. This again, we take the difference between what we predict and the actual value, square it up. That's power in F#, so we bring it up to second power, square it up, and we just sum it all after all. So I'm just gonna have that function too generated, and we'll need charts to compare how good we're doing, just to see the progress. So the chart of the actual data and our prediction. So let's take just the data from the alcohol values and the labels or quality, which is our right answer for this problem. And let's take sample W, which is 1, and B 0. So we're looking at 45 degrees linear function here. And calculate cost function for that, and just draw the charts to see how it looks at the basic data. So that's our actual data, and that's our prediction if we use the w equals 1 and b equals 0. The scales for the horizontal and the vertical are not the same, so it doesn't look at 45 degrees, but you can see it's linear function. Alright, so now our task is to find the way step by step to get into aligning with our data, to have like the least possible error. And yeah, we also calculate cost function, so let's see what's the value of this. It's let's just run it here. Yeah, so it's 11. We want it to be close to 0. 11 is very big. Somewhere between 0 and 1 would be respectable. So we're gonna look into how to can do it. And there are multiple ways to optimize algorithm. But the one we're gonna use is called gradient descent. So now we have two parameters, a and b, or w and b, as I mentioned previously, that cause that define the cost like the shape of our function, and also depending on those two parameters, the cost, so how far our function is from the like middle of the data, will have different values. So for some of the parameters of a and b, the cost will be really big. Like right now, the cost is really big for what I show you, and we want to find value of the b and I that is somewhere like gives the bottom of this ball, so the lower of this algorithm. So the algorithm of gradient descent is sort of starting at the point we're starting, and we want to find the bottom of that ball. And you use it for each dimension. So right now we have two parameters to feed a and b in our function. So we'll do it separately for each direction because it's just easier math. And for each of those dimensions we have to calculate the derivative of the function. That's another mathematical term, which is sort of finding the way of change of the cost for every change of the weight. So if we change the weight a small piece of just a tiny bit, if the change of cost is big, then the derivative is steep, and if this change is smaller, then the derivative is less steep. We're looking at finding derivative is this flat because that means we're on the bottom. So if the derivative is steep and negative, this means that we have to go a big step into positive sign. If the derivative is like not so steep and positive, we need to use the negative sign. And we also need to do our steps in right size, because if you do too big of the steps, it's called the steps we're doing, it's called learning rate. So too big of the steps will cause that we'll never get to bottom of that value. We'll be just not finding the best fit of the function. And the small learning rate means that it's gonna take a lot of time. So it's also finding a good value for learning rate is also quite important. It's sort of you do by experimenting. Things like learning rate or number of steps we're gonna use are called hyperparameters, because those are parameters that used to calculate the actual parameters of the function. And hyperparameters are things that with linear regression we have usually two hyperparameters, which is like learning rate and number of steps. When you do like bigger designs, for example neural networks, then the architecture of neural networks are also hyperparameters. So like how many layers you have, how many nodes per every layer, and so on. Let's try to run this gradient descent right now with the code ahead. So those are the functions for calculating the derivatives. I'm not gonna go deep into this how it's done, just to not lose the focus about it. in real life you don't really need to do it. I'm just gonna show you some another way to run those things. And if you just run things in code like me right now, there are built-in libraries for just calculating derivatives for any function, so you don't really have to like do it manually. And here's my hyperparameters. So this is like the learning rate. I just picked one that works. It took me some like half hour to fit those numbers to be okay for this case. So it's like now perfectly fitted to have a nice demo. But usually you'll have to like just find them. And usually learning rate is somewhere between 1/10 or 1,000 of like number scale. And learning steps, it really depends. For some algorithms it's gonna be like tens of thousands for steps usually when you like train neural networks, but for this problem it's relatively easy, so 150 steps was just like enough. So I'm gonna now run this for loop, which is like for every step we calculate the step into middle of the ball for each of the parameters, so for W and for B, and we update the new the W and B of the new values, so just basically getting step down. And every 10 step I just draw the chart, so we don't do it like 150 times, but like 15 times. I really wanted to make it animated because I forgot to run the lines above here. I really wanted to make it animated, but because I didn't, so I'm just gonna animate by clicking. So that's the previous chart we drawn, and that's where we start. We start with 0, 0, so it's a flat line on the vertical. So with every 10th step, you can see like we're getting closer, and you also see that the steps, the speed we're getting is slower. So with as I said, the gradient descent work that way, that you do start with like big steps, but the closer you get smaller and smaller steps. So we pretty much like fit the data very well. So now we can look at the test cost and compare short on the test data. So this is the other chunk of data that I haven't used for training data, and see how it did on this data, and see that also fit pretty well. The cost function here that we have right now is what's the test cost? It's 0.27, so it's like much better than 11 something we had previously. And let's see what's W and B. So our function that we end up with is W is 0.6 times so this is our function to defining how good a wine is based on the alcohol value. So if you have a wine that has 10% alcohol, it's gonna be 2.6 plus 2.69, so it's gonna be something like I don't know, 5.2 in the scale we had, which is like 1 to 10, I believe. But we all know that it's not all about alcohol. That just there are more things to the good wine than just the amount of alcohol, and that's because and we need to find like usually a better way to fit the data and use the more of parameters. All right. And because I don't really want to do a lot of those calculations, I'm gonna show you the same example, just solved with Azure ML Studio, which is sort of the way you can do the same thing without coding. Azure ML Studio is also available without Azure subscription. You don't need any MSDN subscription or anything, and the basic tier is for free, so any of you can just create an account and just play with it here. So what I did, I Can you see this? Yeah, I'll just put it maybe more full screen. So what I did here is rebuild the same flow, but you had this sort of visual editor to do it. So I started with I uploaded my data set with the red wines, exactly the same I showed you. And it's really nice with Azure that you can visualize every step, so you can look at this data in this way. And this also shows you that histogram of all the data, so you can sort of see the shape of the data and see the values and so on. Just some way to go through how much of the data is. You can see that there's like 1600 or nearly 1600 rows here. I added the steps to select the columns, because in the example I showed right now I just use alcohol. So let's run it first with just only using alcohol as the data. We'll run it with Azure, see what the results are, and then rerun it algorithm, but using all the data, and see if it's gonna get better or worse. Hopefully it's gonna get better, because generally the more data you have, the better algorithm you can build. And I'm also gonna split the data to this like evaluation, the same we did. Azure just used the different logic, it shows percentage, so to get like exactly 1000 it's 62.53%. Just something I had to dig. And another step we can actually visualize, as like I showed on every steps we can visualize. So because these steps give us output of in two form, we can see like first data set, that's 1000 elements, and second, that's gonna be the rest. Cool. The next step is the train model. So this is like the moment I used with the gradient descent, everything. So the training block gets two inputs. One of the inputs is the data we want to train on. The second is algorithm. So I'm using linear regression, and I'm gonna just use default values here because I don't know those very well. This is different optimizer, it's a least squares, but it doesn't really matter. The same method is just a different method for finding the functions that matching our data. So let's run it all to see how long it take, just to give a feel. I ran it before, so that's why it's all green, but you can see those clocks when it's being evaluated and the green tick when it's done. So it's pretty quick, but it's a small data and it's a simple algorithm to do it. That's the free tier of Azure, so also the least powerful machine. So even with that, it's pretty okay to work on simple models. All right, let's see visualize the train model, and this algorithm gives us slightly different values. So it's alcohol, or our W is 0.36. So just okay, remove the old one, but this is like 0.6 alcohol plus 1.8. So the curve they came up with is a bit flatter, but or no, actually steeper, but moved at the lower over the axis. And now we can use the data we put aside, the testing data, to score the model, see how good it went. And scoring gives us actually the answers we calculated. So for the alcohol, that's 11, and the quality that was original, we predicted 2.8, so it's 6, so not so great, but for this is actually okay. So we can actually see how it would be for the data it's already seen. So this is actually predictions on the data. No, it's actually in the test data, so the one that it hasn't seen. But it compares the quality, which is what was the right answer from the answers we gave it. And also, apart from scoring, we can do evaluating, which gives us a bit more statistical data on how we did. So, for example, the error and so on. So let's see those. And the root mean square error here is 0.68. It's actually bigger, the one I did. It's probably because the one I did with code, I spend a lot of time to find the good parameters that are gonna work well, and here I just use default values. So with default values it did okay, but not so great. But see, with pretty much non-effort we did some prediction already. Now it's gonna be, you can take some time to just fit those hyperparameters and find the better values. You can also like replace the algorithms, so for example use neural networks and you know, define them and so on. There are a few other algorithms to do regressions to solve this problem, and you have algorithms for other things, so like classifications, recommendations and so on. So this is like really cool thing to just start digging into machine learning and have this like visual flow of data, and you know, play with this, and you can just start reading somewhere in literature on the internet what those algorithms means and if they're good for you or not. But you can pretty much start with knowledge that's maybe not zero, but not very big. Okay, so let's ignore this step with selecting column and take all the data we had so far and train this algorithm to use all the features we had. So not only alcohol, but also acidity, density, and all the other things that we can measure in wine. So we're gonna start this algorithm to rerun on all the data. It's probably gonna take slightly more, but not, shouldn't take much time. Yeah, it's very quick. And let's look at our train model, how it's gonna look right now. So now we have a lot of parameters, so it's not only alcohol, but multiple others. So we can take all those things into consideration and draw a function. It's just gonna be really hard to visualize it because now we're not looking to 2 dimensions or 3 dimensions, but like 10 or 11 dimensions. So it's impossible to visualize, but mathematics still scales up to those 11. So that's really nice. That's usually later you don't really visualize this data because for real data sets you use not 10 parameters, but like for example 400 parameters or so on. There's a very interesting data set available, for example, for all the apartments sold in London in last 20 years, and there's like a lot of parameters about its location, number of bedrooms, square size, number of windows and things like that, and you can play with this data to try to evaluate what's the model for pricing apartments. And if you do like image recognition, each of the pixels is one of the features you use for so for pictures that like 20 by 20 pixels you have already 400 parameters. If you have image like I don't know, like 4K, then you have like millions of parameters to feed into. So it's like that's where the problems actually started getting in machine learning. The math is still the same. You do some form of fitting functions, but you have just like loads of data to do it on. Alright, so let's see how good was the score with this added information. And now our root mean square is 0.60, so slightly less, but still the function I did with just matching parameters did better. So this also showed that having a lot of data is nice, but you also need some time to spend to like use proper algorithms and give them some good parameters. Alright, let's get back to slides. I have just some few more notes. So yeah, so what we did basically, we fit straight functions that data that is not very straight, and it's called underfitting. So our algorithm gives some decent results, but we could do much better if we just do function that's maybe not linear, but maybe more complicated. This is where neural networks come, because neural networks, what they do in effect is pretty much create a more complicated function. And but if you fit your function, you don't want to get too good to have like this overfitting. This is what I said, that's why we split the data also, because you want to have algorithms that's general and not too good, because if you get some point, for example, here, it probably wouldn't work well with this wine getting too windy. All right, this is it from me, but I'll take questions or not. All right, we can also talk over a beer and pizza later. No worries. I also create some little website, like page on my blog with some links for further reading. There are some cool algorithms, or where to start, and how to do data science if you suck at math, and a few other articles that are really good introductions. And yeah, thank you for coming.